Okay, so I want to start discussion 7.1. We're going to talk all about energy. So what is energy? Energy is the capacity to do work or produce what is known as heat. Now, heat is not the same thing as temperature. Heat is thermal energy that will flow between a system and its surroundings. Now, the units of energy will usually be in joules or kilojoules, which is just 1,000th of a joule, right? There's 1,000 joules in a kilojoule. You could also see it as calories with a little c or calories with a big C. And calories with a big C are what we see on our food labels. So the system is what is actually happening. Now, it doesn't matter if that is a physical or chemical change, but the system is what is occurring. And the surroundings are the area that contains the system. So one example is me burning wood in my fireplace. The wood burning is the system, and the surroundings of that reaction are the room where the fireplace is. We feel the heat is being released to the surroundings from the system. Okay, so endo and exothermic changes. An exothermic change is which energy is released to the surroundings. So the example of burning wood is an example of an exothermic change because the energy of the system is being released into the room. So in an exothermic change, you're going to see the temperature of the surroundings increase because heat is being given off by the system. Now for an endothermic change, we have a change in which energy is absorbed from the surroundings. So in an endothermic reaction, the change in temperature of the surroundings will decrease because energy is being removed from the surroundings. Okay, so enthalpy level diagrams. Enthalpy is denoted with a capital H. And the definition of enthalpy is the total change in energy during a reaction. Now we call enthalpy delta H because delta H is specifically the change in energy, and that Greek letter delta represents change. And activation energy is denoted with a capital E with a subscript of A. We looked at this in Unit 5. And activation energy is the amount of energy required to initiate a reaction. So we can quantify both of these things by looking at what are known as enthalpy level diagrams. And an enthalpy level diagram is an XY plot. On the y-axis, we'll have energy, or enthalpy, and on the y-axis, we have time. So for an exothermic reaction, the general shape of the graph is like this. And for an endothermic reaction, let me just label my axes here. The graph will look more like this. Now when we look at this, we see two horizontal lines, and they are at different values on the y-axis. So each of these horizontal lines represents a specific amount of energy. The first horizontal line represents the energy of reactants, and the second line represents the energy of the products. Now, since the delta H is the total change in energy during the reaction, the area representing delta H will be the difference between the energy of reactants and the energy of products. Now, if we look at this actual shape of this graph, we see that the energy is remaining constant, and then we go up over a little hump. Once we go over the hump, the reaction proceeds toward products. So this little hump is actually what is the activation energy. So the activation energy is represented by the area, the line between the energy of reactants and the top of the hump. So if we're given numbers on these axes, we can actually calculate or determine the numerical value for delta H or activation energy by looking at the differences between those two regions on the y-axis. So for an endothermic reaction, it's the same thing. Delta H will be the region between the energy of the reactants and the energy of the products. And the activation energy will be the area from the reactant line to the top of the hump. Now you notice in an endothermic reaction, the activation energy is much greater. That's because in an endothermic reaction, energy needs to be absorbed by the system before the reaction can take place. Now, it's important to note we're never going to start measuring our value for delta H or activation energy from the origin of the graph, it's always going to be starting at the reactant line and either going to the product line for delta H or the top of the hump for activation energy. Now for an exothermic reaction, delta H will always be negative because energy is being lost by the system. And for an endothermic reaction, you'll always have delta H being positive because energy is being gained. So if you just see a value for delta H, you'll know that the reaction is exothermic if that value is negative, and you'll know that it's endothermic if the value is positive. So let's do a little practice. Here we have an enthalpy level diagram. Now, the first thing I want to talk about is whether this is an enthalpy level diagram for an exothermic reaction, or an endothermic reaction, excuse me. So if I look, I have a line here representing the energy of reactants and a line representing the energy of the products. Now I see that the products have more energy than the reactants. That means that energy must have been gained during this reaction. So if we want to determine what the activation energy is, again, we go from the line representing the energy of reactants to the top of the hump. The top of the hump is at an energy of 400, and the energy of the reactants is at an energy of 100, so the activation energy for this reaction would be 300 joules. Now again, we're not going from the x-axis, we're starting at the energy of the reactants. And delta H, the change in enthalpy, will be represented by line C here, and so line C starts at 300, or it tops out at 300, and goes down to the reactant line, which is 100. So delta H will be 200 joules per mole. All right. Okay, so we can determine if a change in state is exo or endothermic by looking at the motion of the particles before and after the change. So slow-moving particles will have relatively low energy compared to faster-moving particles, which will have relatively greater energy. Right? So if the particles began moving faster during the change, that means they started out slow and became faster. We can infer that they gained energy. So that state change would be endothermic, because the definition of endothermic is a process that absorbs energy. Now, if the particles began moving slower during the change, in other words, they started fast and slowed down during the change, we can infer that energy was lost, so that change would be exothermic, because exothermic reactions are one in which energy is released by the system. So let's actually look at these state changes and their names. First, we have freezing and melting. We know freezing is going from, oh, I got these backwards. So melting is going from solid to liquid, and freezing is going from liquid to solid. Okay, sorry about that. So if we look at melting, we're going from solid to liquid, right? So if I have to compare the energy of the particles in these samples before and after the change, and again, the arrow represents the change. So the relative energy of solid particles is lower than the energy of liquid particles. So I'll just put an L and an H to show low to high. If the speed of the particles increases during the change, then that means it is an endothermic change. Now, that's not too hard to imagine. You have to put energy into ice to melt it into water. Now, freezing is a little bit less intuitive. It's hard to imagine just by thinking about it whether freezing is endo or exothermic. So we're going to look at the motion of the particles before and after the change to determine what happened. So we know that solids, again, will have a lower relative energy compared to liquids. So we're going from high energy particles to lower energy particles, fast to slow. That means we can assume that energy is released during this process, so freezing is an exothermic change. Now let's look at boiling or evaporation. Now, boiling and evaporation are the same thing. Boiling is just rapid evaporation. Now we know that boiling is going from a liquid to a gas. So we know that gases have higher moving or faster moving particles than liquids, so they will have a higher energy. So we're going from low energy to high energy. So we can infer that energy was gained, and so this is an endothermic change. Now, the opposite of evaporation is condensation. That is a gas forming a liquid. So here we're going from high energy gas to lower energy liquid. If we're going from faster to slower particles, we can assume that the liquid particles have less energy than the gaseous particles, so energy must have been given off, and so that is exothermic. I want you to take a moment and pause the video and look at sublimation and its opposite process, deposition, and determine whether these changes are exo or endothermic. All right, so if I look at sublimation, the definition of sublimation is going from the solid phase directly to the gas phase without passing through liquid first. Now we know gas particles have high energy and solid particles have low energy. If we're going from low energy to high energy, we can assume that energy must have been absorbed for the change to occur, and so it's endothermic. Now, the opposite process of sublimation is called deposition, and that's going from a gas directly to a solid. So here we're going from high energy particles to low energy particles. If the particles have less energy after the change, we can infer that energy must have been released to make that change happen, and so that would be an exothermic process. All right, so here's the heating curve of water. We can actually use this heating curve to show these state changes. Now, if the state of our sample at negative 20 degrees is solid, that means that all during this line, our state of matter is solid. Now, once we get to 0 degrees Celsius, the line flattens out. Now, when the line flattens out, what's occurring there is melting. Right? Now, once we are melting and all melted, we have liquid, and so we see the temperature start to change again. So this diagonal region could be labeled as liquid. Once we get to 100 degrees, the line flattens out again, and what we have occurring here is called boiling. And then finally we have gas up here, and the temperature can just rise indefinitely. Right. So melting represents an endothermic process. We have to put energy into a sample in order to melt it. So when we're melting, we're going up in energy, so that's endothermic. The opposite process would be called freezing, and we see that freezing is represented by a down arrow here, so we can show that it is exothermic. Any process that's endothermic, its reverse process will be exothermic. So here we have boiling. We know that we have to put energy into water or anything to boil it or to evaporate it. Well, the opposite process is condensation, and so condensation will be exothermic. Okay, so molar heat of fusion and vaporization. The molar heat of fusion the definition is the amount of energy required or released when 1 mole of a substance melts or freezes. Now we know that if energy is required to melt something, and energy will be released when we freeze something. And the molar heat of vaporization is the amount of energy required or released when 1 mole of a substance evaporates, or its opposite process, which is condenses. I think I spelled that right. Now, the units of molar heat of fusion will either be joules per mole or kilojoules per mole, or you'll see something like joules per gram or kilojoules per gram. All right, so let's practice. The question says the substance has a molar heat of vaporization of 498.2 joules per mole. How much energy in joules is required to vaporize 3.5 moles of this substance? So the problem tells us that we're looking for joules. Our answer has to be in joules. And we have a unit of joules per mole and a unit of moles. So the question becomes, what would we have to do to those numbers in order to get moles to cancel out and have our answer be in joules? And the answer is to multiply the two numbers together. So when I take 498.2 and multiply it by 3.5, hang on, I was putting this in my calculator, we get 1,744 joules. All you have to do when we do these problems is multiply the two numbers together. So take a moment and pause the video, practice the next one all on your own. All right, so the next one says a substance has a heat of fusion of 102.2 kilojoules per gram. How much energy in kilojoules is required to melt 10 grams of the substance? So again, all we have to do is multiply the two numbers together. So if I take 102.2 kilojoules per gram and multiply by 10.0 grams, the units of grams cancel, we'll be left with kilojoules, and we get 1,022 kilojoules. All right, so these problems are really easy. Generally, when you see them on SOL or a test in our class, all you have to do is multiply the two numbers together. Make sure you give the appropriate unit. All right, so thermochemical equations. The delta H value for a reaction can be given in the chemical equation for the process. So for an exothermic reaction, heat will be given off, so it will be shown as a product of the reaction. And an example of that is what we call the Haber process, the creation of ammonia from nitrogen and hydrogen. When we look at this equation, we have the part of the equation that we're used to seeing, just the reactants and the products, but an additional product is an amount of energy. If you see energy as a product, that tells you it's an exothermic reaction. Now you could also see just the regular equation with a delta H value given to you. Now since this is exothermic, the delta H value will be negative 253 kilojoules. It's negative because delta H is negative for exothermic processes. So for an endothermic reaction, heat will be absorbed and it will be shown as a reactant of a reaction because energy is needed to get the reaction going. So an example we have down here is the boiling of water. We're going from liquid water to gaseous water. So we know that that is an endothermic process, so we have to put energy into the water in order to make it boil. Right? So in this case, you could also see delta H written aside as just 6.01 kilojoules because it's an endothermic change, the value will be positive. All right, finally, specific heat. Specific heat is the amount of energy that is needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. All right, so that means the lower that something's specific heat is, the less energy, the less energy will be required to change its temperature. All right? So things like metals will have low specific heats because they heat up very, very quickly. Things like water have high specific heats because comparatively it would take a lot more energy to heat up water than it would an equal mass of a metal. So the example we used in Unit 1, at the beach, the sand will heat up a lot faster than the water because the sand has a lower specific heat than water. So here's a little practice. It says, which metal would experience the largest temperature increase when 200 kilojoules of energy are absorbed? So we see these different values for specific heat. Whichever one has the lowest specific heat will experience the largest temperature increase if an equal amount of energy is input. So in this case, lead will experience the largest temperature increase. Aluminum, because it has the highest specific heat, will experience the lowest temperature increase. All right, so we can do calculations with specific heat. We remember our formula for doing so is Q equals MC delta T, where Q is the heat in joules most often, lowercase m is the mass in grams, and C, the lowercase c, is the specific heat, and it has the unit of joules per gram degree Celsius. So we can use this formula to calculate the energy given off during a chemical or a physical change. You could also use it to calculate any of the other factors that make it up. In other words, you could be given Q, you could be given M and delta T, and be asked to solve for specific heat, which you could just call X, your variable. But the bottom line is, with this equation, you'll always be given 3 of the variables and be asked to solve for one of them. We have to remember, though, that delta T is a change in temperature. So for these problems, you will be given a final temperature and an initial temperature. To find the change in temperature, you have to subtract one from the other. All right, so here's an example. It says how much heat is required when 1,255 grams of water is heated from its freezing point at 0 to its boiling point at 100, and it gives you the value for the specific heat of water. So consider what your variables are and plug them into the equation. All right, so we know that the equation is Q equals mc delta T. It's asking us for Q. It gives us a mass of 1,255 grams. It gives us a final temperature and an initial temperature, so it gives us delta T, and it gives us the value for specific heat. So to solve this, I'm going to take 1,255 grams, multiply it by the specific heat, which is 4.18, and multiply that by the change in temperature, which will be the final temperature, which is 100, minus the initial temperature, which is 0. And when we do that, we get 524,590 joules. Now, this is a rather large number, but that's okay. A joule is a very small amount of energy. All right, the next example, I want you to do all on your own. It says a 155 gram sample of an unknown substance was heated from 25 to 40 degrees Celsius. In the process, the substance absorbed 5,696 joules of energy. What is the specific heat of the substance? All right, so it's asking us for specific heat, which is lowercase c. So when I plug the values into my equation, Q equals mc delta T, Q is energy or heat in joules. So we're going to have 5,696 being equal to the mass, which is 155, times the specific heat, times the change in temperature, which is final minus initial, so 40.0 minus 25.0. So now we just have to solve for specific heat. So let me go ahead and do that in my calculator. And I get that the specific heat is 2.45, and the unit of specific heat is joules per gram degree Celsius. Remember, we always have to have our units. All right, well, that is it for discussion 7.1. Bring any questions you have to class, and as always, thank you for watching.